different accuracies in the solutions that we obtain. And so today what we're going to do is looking at another couple of classes of algorithms. So first of all, using neural networks to solve inverse problems directly. And then finally, another class called normalizing flows. And just like SVGD and ADVI, these have also come out of the machine learning community. So these are new types of methods, or neural networks aren't new, but invertible neural networks are. And normalizing flows certainly are new methods to solve these types of Bayesian problems. Overall, we're not going to reach a different conclusion from yesterday in the sense that we're going to find these different methods have different efficiencies and different accuracies. And so finally then today, what I'll do is try to bring all of this together into one theory that uses multiple algorithms, multiple parameterizations, and so on to answer specific scientific questions. And it'll provide optimal answers in the sense that they are minimally biased. And that is the overall goal of this two-day seminar. I should say yesterday, it was really nice to receive all the questions from the students and perhaps staff, I'm not sure. So please do feel free to ask more questions today. And if that means we have to cut down the talk time, that's fine. Much more important when you get your questions answered and learn something from us to help in your studies. So what we'll do now is we'll just move on to the invertible neural networks and normalizing flows part of the talk. And I'm going to put these together for reasons that will become clear when as we go through. So I'll just open this up. So for this part of the talk, I'd like to give particular credit to Xubin Zhao and Xin Zhang. And Xin on the right, you've seen yesterday. So Xin was a PhD student previously and is now a postdoc in my group. And Xubin on the left is a current PhD student. And they're both working within the Edinburgh Imaging Project, which is logo explains that logo top right. It's an industrially funded consortium for research into imaging problems. So in this part of the talk, what I'm going to do is again summarize just from yesterday the Bayesian inference or problem that we're trying to solve. And then we will look at these two classes of methods, invertible neural networks and normalizing flows. And I'll use similar kinds of examples to yesterday so that we can compare them to the results that we saw yesterday. So 1D depth inversion and 2D travel time tomography, including some real data, again, from across the UK. So the Bayesian problems that we're trying to solve essentially revolve around some kind of forward function that typically looks something like this. This relates model parameters M to the data that we might be able to observe. And relationship between them is usually some nonlinear function, which we call the forward function F. And while traditional approaches to solving this problem, in the sense that if I record some data, I'd like to find out what is the family of models that fit the data. Traditional approaches would be to try to find this solution, M hat, which is the model which minimizes the difference between the predicted data and the observed data. And that's what this arg-min stands for. So this, reading this mathematics out, it means M hat is the particular M which gives the minimum value for f of m minus d. So this misfit between the observed and the predicted data, where the prediction is made by this forward function. As we discussed yesterday, the reason that I'm not so interested in this model, M hat, is that given that we're dealing with continuous problems, the probability that M hat is true is zero, identically zero in every single problem with continuous parameters. And so immediately you find M hat, you have to start asking yourself, well, okay, I found it, but how far is the true solution from M hat? And does M hat have any value at all? It only has value if it's close to the true solution. So we have to then start assessing the uncertainty anyway. So rather than trying to solve that problem, I'm going to directly go for the problem, which is the more general one, which is finding all or a representative subset of the family of models M, such that the misfit between the predicted and observed data is acceptable in some sense. And that really acceptable here really means that the predicted data fits the observed data to within their uncertainties, to within the measurement uncertainties. And the way that we formulate this problem is using Bayes' theorem, and what we and this quantifies what is acceptable or unacceptable in this posterior probability density on the left. So this is what we're trying to calculate. It is the probability that any particular model is true given the data that we've observed. Okay, so that summarizes whether models are more or less acceptable. Are they consistent with the data, or are they not consistent with the data? And that probability will tell us. If they're consistent, well, there's a reasonable probability they're true. If they're inconsistent with the data, that probability will be close to zero. And Bayes' theorem, just to remind you, comprises these three terms: the likelihood term, which assesses the data fit; the prior term, which doesn't depend on the data, and this is another probability distribution that represents our prior information, so the information we have independently of the data. And then the term on the bottom is the evidence, and this doesn't depend on the model. And the main property of this term that we're worried about, or the two main properties, the first is it acts as a normalization constant, which means that this whole set of three terms is a valid probability distribution because they equal this probability over here. And so they have to integrate to one. That's a property of all probability distributions. So that's the first role of the evidence. The second point about the evidence is it's extremely expensive to calculate. And so whatever algorithms we design, we try to design an algorithm that will give us this solution without ever having to calculate the evidence explicitly for any particular models. So that's our goal. Our goal is to calculate this posterior, or to estimate statistics of the distribution, whether that be mean, variances, marginal distributions, correlations, so on. And in particular, for the first part of this talk, I'm going to ask, can we estimate this using neural networks? I'm getting a little bit of feedback over here. Maybe somebody needs to mute their microphone. It'll just be better for everyone. Okay, so let's just start with a brief introduction to neural networks, just in case there are some sort of early years students who are on the call here who haven't seen much about neural networks. So they're typically structures that generically look something like this. They're a graph. And the graph, there are nodes of this graph. These are the circles, and there are edges, which are these connections. And you can see that what we have here is an input layer, if you like, this sort of vector of nodes on the front, and an output layer on the left, and an output layer on the right. And to get from the input to the output, we can go along these various paths, which are the edges. And neural networks are structures which, as you can see here, are somewhat complex. They're deliberately complex, but they're constructed out of very simple operations. And that is deliberate, as we'll see. So the kinds of operations that are typically used, we'll have the input variables here, and this xi just represents a vector of values. One will go into each of these nodes. And then each of those values will be passed down these connections here towards the central nodes. And this sort of nodes in the middle is called the hidden layer. So we've got the input layer, output layer, and the hidden layer in the middle. Now you'll see that each of these connections here has a weight attached to it, and it's represented by this matrix of weights. So this Wij is the weight between xi and hj. And the input values x are passed through these weights and multiplied by them. And when they arrive at a node, each of the nodes has another number associated with it, which we call the bias, bj, and the bias is added. And so if we look down at the bottom there, we see that the values h, by the time we get to here, are the input values multiplied by the weights and offset by the biases. And so we have this linear combination of the inputs. Now that linear combination h is then passed through some simple function, which we call the activation function. And there are different functions. You can use almost any function you like, as long as it's you can calculate its derivative typically. And for example, this LU function is the one that's shown over on the right there. It's a very simple function. It does absolutely nothing when the inputs are significantly negative. And then for input, it transitions to give you a linear output. Very simple function. And that's just to provide some non-linearity to the structure, to make the structure more complex and non-linear. The outputs of this are hj dashed, and they're then passed into another set of connections with weights and biases, and so we get another linear combination of those outputs of the activation function. And that gives us our final output to the network. So this kind of structure is useful because it is complex and because it is nonlinear. And the reason is that we typically use neural networks to emulate other functions. So clearly this is just a set of linear operations and then simple nonlinear ones. It's very rapid to calculate. If given an input, we can calculate the output very rapidly. If we can make this structure, which means, and the terminology is train this structure to emulate a particular function that we want, then it will give us a very rapid way to calculate it. And the training process is the updating of the biases and the weights and the activation functions and the number of nodes in the hidden layer, for example, so the number of connections. That is what we do in the training. We update the weights and the biases and the structure to best emulate any particular function we're interested in. And so in geophysics, we might be interested to emulate a function where we take in, say, the dispersion curves, which means that we calculated yesterday. So these are, for example, the speed that surface waves would travel when the surface wave has different periods of oscillation shown on the horizontal axis. So for a period of 1 second, the surface wave would travel more slowly than for one with a period of 3 seconds. And so we made maps of these different velocities yesterday. And so for any particular geographical point, we could pull out all the different, from all the maps, we could pull out the speeds that the surface waves are traveling across that area. And we might want to train the neural network to take these data that we have available on the input side, and on the output side, emulate a function which gives us a pure wave velocity structure with depth beneath that geographical point. That is the kind of problem that we have used neural networks for in the past, and quite successfully. That works pretty well for this problem, and I'll show you an example later. Now, what we may find is that when we try to emulate or train the network to emulate a function like this, that it's not complex enough. And so we have to start varying the structure of the network. For example, we could add more layers to make it more complex, more nonlinear. We could make the layers larger to give more edges, nodes and biases and weights. And we could change the structure of the connections in here, so we could have them looping back on previous layers, for example. We could have special structures to the interconnectedness and convolutional networks. And we could have the training of these networks, the updating of all the structures and the weights and the biases using different algorithms, such as adversarial algorithms, or there are a whole load of different structures that one can have for these networks. but really the main aim of them is to emulate, allow us to emulate some relationship. Now, if we could train the networks to emulate a function that went from dispersion curves to a velocity structure, that would be great, but we know that that's not possible. We saw this yesterday. For any particular dispersion curve, there's a whole family of models which will fit that data. And the problem with this kind of structure is that there's no uncertainty information provided on the output. Even though this is a non-unique problem, we cannot output uncertainty information on that side. So given that, we're not going to use this standard network structure. This is called a feed-forward network for obvious reasons. Here it's just feeding forwards from one side to the other. We're not going to use this kind of standard network alone. We're going to put it inside another structure called a mixture density network, or at least that's one way to do this. In fact, the talk here today is going to be on something else, but this is what we have done for the past decade, and it gives pretty good results for many problems of interest. So if we want the mixture density networks, which are a structure around the neural networks, to give uncertainty information, the first thing is we have to allow the networks to parameterize the uncertainty. And we're going to do that using what's called a mixture of densities. And hence the name MDN, mixture density network. And so the way that we parameterize any probability distribution is as a sum, which is what mixture means. The mixture refers to the sum here of some sort of elemental kernels of probability densities. And these are just going to be simple distributions like Gaussians, normal distributions, or anything else we like to use. We will use Gaussians. And it's a sum of those normals weighted by some numbers alpha k. So that's going to allow some have higher weight, lower weight in the sum. And the reason that we use this parameterization is that there's a very nice property in that if we use a sufficient number of Gaussians, here we just use 3, they've got different weights, which gives them different amplitudes. And if we sum them up, we see that we get this probability shown in black. And the property of this mixture density formulation is that if we use a sufficient number of kernels, the Gaussians here, with appropriate weights, we can represent any distribution that we like, any accuracy that we choose. So that's why it's a very flexible and nice representation of probability distributions. So that is the formula we're going to use to represent the probabilities. Now we want the neural networks to give us probabilities in that form. We're still going to take the dispersion curves in on the left-hand side. Those are our data, so that's what's going to go in. But on the output side now, we're not directly going to give the models. We're going to train the network to give the parameters that define the kernels and the weights. So here are the weights that will be part of the output vector. And then for the normal distributions that we're going to sum up, the Gaussians, we're going to need means and variances or covariances. And so that will train the networks to give those outputs. And then we can simply take the Gaussians that those outputs define and sum them up with the appropriate weights to get our estimate of the probability distribution. And we've shown in a number of previous papers that this is very easy, in fact, or it's relatively easy to train neural networks to output this kind of representation. So for example, if you have a network that is outputting anything that you've already got a structure for that network and you've got a code to train that neural network to output velocities, you can change it to a network that outputs the uncertainty in the velocities in this way with just an extra 3 lines of code. It's very simple to do, and it's worth trying if any of you are working with neural networks. Just look up mixture density networks, or you can look at the papers that we've written or others have written and see how to update your code to output probabilities in the answer. And so, for example, most recently we've used this for 2D travel time tomography of the type that we've been looking at in this seminar yesterday, and we will be today in this paper, for example. So, given that we've done that, why am I not using them today? The reason is that these mixture density networks are very good at giving means, variances or standard deviations, and marginal distributions, but they're quite hard to train to give you the interparameter correlations in higher dimensional problems. At least we find them quite hard to train. And so we've been looking for an alternative that would help us to obtain these parameter correlations as well. So for this, we're going to look for a new structured neural networks called invertible neural networks. And this was just, these were just developed in 2018 by our Ardizoni and others. And we've just been testing these out in Geophysics in that paper that's left. And the nice thing about these invertible neural networks is they allow us to approximate the posterior distribution with the correlations. And as the name suggests, these neural networks work both in the forward direction and simultaneously in the inverse direction. So they get trained in both directions at once. And I'm going to show you what these networks look like and how we train them. So this is the structure of these networks. This is the sort of elemental structure, or canonical structure of them, which is quite different from what we were looking at before. So the input is on the left and the output is on the right, at least to begin with. We'll think of it that way around. And the input will be a vector of numbers, and we split it into two parts, x1 and x2, typically equal parts, but they don't have to be. And then these two subvectors go along these edges in the graph. So x2 would carry along all the way along until it gets to this operation here. But at the same time, it will also pass up these two branches here, and they pass through two functions, S2 and T2. And these can be any functions you like. It really doesn't matter. The only constraint is that they have, the output has the same dimensionality as x1, so the same number of elements. But other than that, there can be any nonlinear functions that you like, or even linear. When they get the up to this branch up here, the output of S2, so S2 applied to the inputs x2, are taken to an exponential, and then they're multiplied element-wise with the numbers x1. So basically each element in the vector of x1 is multiplied by the vector and the output of that function. And then they are added to the output of the function t2. And that then gives us this sort of halfway stage output y1. So we've gone from the input, which is x1 and x2, to a case where we've got x2 still down here, but up here we've now got y1 given by this simple formula here. Now y1 just continues right over to the end of the output, but it also goes down these two branches where exactly the same kind of operation happens again. So y1 is passed through s1, it's then exponentiated and added to t2 to give us y2. And there it is written down here. y1 passed through s1, exponentiated, multiplied by x2, added to t1 to give us y2. And then we have the two outputs, y1 and y2, which are and they're just concatenated, so put one above the other to give us the output vector. That's what the neural network, this invertible network does, but why do we have this structure? Well, it's got a very neat property, and that is that I convert these two equations just by rearranging them. So if I just literally rearrange these two equations, I get two equations over here where I can take the output vector y1 and y2 and plug them into this lower equation to get an estimate of x2. And then I can plug x2 into this top equation together with y1, which we have, to get x1. And what you'll notice, therefore, is that this set of relationships is no more complex than the ones on the left, and it takes the output over to the input side. And what's more, it does so, even though we're going in the inverse direction, we don't have to invert or look at the inverse of the functions t1, t2, x1, and x2. We're still using them in the forward direction. This is a very neat property of this type of function. And it's true, even though S1 and S2 and T1 and 2 can be any functions, they can be arbitrarily complex. For example, we can use fully connected neural networks, as we were looking at previously. Convolutional neural networks, any type of neural network we like, we can plug in to these 4 functions here. And that makes the structure, although overtly simple, actually intrinsically incredibly complex and therefore very flexible. We can use it to fit flexible functions. And we call this structure up here a coupling structure because it's coupling the 2 branches together. So let's see if we can, I'll show you how we train this kind of structure to emulate a particular function of interest. So let's say we have some input, and these might be our model parameters. And so we have model parameters here, which are, let's say the prior distribution is uniform. So that's our prior knowledge. And we take lots of samples of the input vectors. Just speaking about the histogram here, represented by the histogram. And for each one of those, we know what the corresponding output should be. So for example, if the input was dispersion curves, we might, I'll explain how we get these later, but let's say we have a corresponding output y for each of those input variables. And so we're going to have an equally large set of output variables y as we do the input. And this is going to together form what we call the training set. These are a set of examples that we're going to show to the neural network, and we're going to make it update the structure such that it best emulates the relationship between the input and the output variables. Now, that's going to help us emulate the forward function. And in order to do that, I mean, that's just like a standard neural network. So we're going to introduce what's called a loss function. And that is just going to be the misfit between the examples that we have of the outputs and whatever the neural network outputs for any given input. So we'll give the neural network one of these inputs, it will give an output. We work out the misfit between that and the one that we wanted, and that will be this misfit here. And this is a loss function, which basically tells us how bad that misfit is. And we would like to, we can then update the parameters inside here. So the parameters inside these 4 functions, we update them to minimize this difference. And that will make the neural network give the best possible fit to the forward function. And that's the standard way that's done. However, we also want it to emulate the inverse function. Now, the problem with the inverse function in geophysics is typically it's non-unique. Yet all of these operations in here are deterministic. So given one y, we're going to get one x output, not a distribution. So the way that we handle that in the case of invertible networks is we add another set of variables on the output side, y dashed, and this is just a random variable chosen from any distribution we like. So we're going to choose a Gaussian, and every time we input a y value on this side and want to go to x, we will input a random draw from this distribution. This will give us a vector of random values here for y dash. To give us some random inputs to go down this side, and we are going to, we want to train the network so that we were going to have random inputs going in, and that's going to introduce an element of randomness to the outputs coming out on the x side. And now what we want to do is train the network so that as well as fitting the forward function, this randomness is expressed as a sample of the posterior distribution of x given the input y that we gave it. So in the end, we're going to put some data in here, geophysical data. And we want the network to output one sample on the left of the posterior distribution for that data. And so, and every time we run it, we're going to give it a different random draw for y dash, and so it's going to output another sample. And so it'll act a little bit like a Monte Carlo algorithm in the sense it'll give us lots of samples of the posterior distribution, but this time from a neural network. So to emulate that inverse problem, or to ensure that we train the network to emulate that problem, we have to add something to the loss function. And the fairly typical way to do this in the literature is to add some measure of the difference between the neural network applied to the prior distribution on X, applied to all of this function here, this distribution here. If we apply the network to that set of values, we get this distribution over on the right. And but we know what the distribution on the right should be from our training examples. And so this term here measures the difference between those two distributions. Now, yesterday we used a measure of the difference between distributions. We used the Kullback-Leibler divergence. Today, or here, we use a different measure, which is called the maximum mean discrepancy. And it's just another measure of the difference between two distributions. I'm not going to go into that. It's just another way to measure that or to estimate. And it turns out that if we use this loss function, it can be shown that the neural network, if we minimize this loss function, it can be shown that the neural network will approximately output samples of the inverse problem solution, so the posterior distribution in the Bayesian. Now, the only thing so far is we haven't accounted for the data uncertainties. And the way we do that is we add, if we know the data uncertainties, we add samples from data uncertainties on the input side. And that's because if we want to, for any particular input, model X, we want to output the data that would be observed, we need to give, I mean, the network will output the noiseless data, but we have to give it also a sample of the noise so it can output noisy data. So that's why it goes on the input side. And the final thing we have to do is we have to make sure the dimensionality of the input and the output side is the same, because we're working in both directions. We want the same number of dimensions. And so we would pad out one side or other, but typically the left side with zeros, just to make sure that the output and input have the same dimensions. So that's it. We've gone through quite some detail there about the structure, but that's just to give you an idea, because these are quite different from the usual structures of neural networks. Let's see how they actually work. So to train them, what we'll do is we'll construct a training set by starting with a lot of different Earth models that we draw randomly. And so in this case, we're just dealing with a 1D shear velocity model. So this is shear velocity as a function of depth beneath a certain point. And we will use physical relations, not neural networks, so modal approximation physics, to predict surface waves would travel across this structure. And this gives us a dispersion curve. So again, this is a function of period of the surface wave oscillation. Tells us how fast that surface wave would travel. And so for different Earth models on the left, we should have different dispersion curves on the right, because the waves at different periods are sensitive to different depths in the Earth. And so we have lots and lots of examples of those. And if we, in this case, and these are going to be training examples that we show to the network. And so we're going to take lots of those, in this case, 100,000 training examples of pairs of input and output, distributed according to this prior distribution on the left, which translates or maps onto the distribution of phase velocities on the right. Now to that, in order to train the network, we have to add our random variables. These are called latent variables. I should have used that term earlier. This is the random ones that we put in to get non-uniqueness in the inverse problem solution. And we use these distributions to train the neural network. So we've got 4 sub-neural networks in here, T1, S1, T2, S2, and we will update those the weights and biases in all those neural networks using fairly standard methods to best emulate both the forward and the inverse function. Now, once we've done that, we'll have a trained network which we can test. So let's test it. So here is something, here's a particular random model. Let's say this was the true model in the Earth. If it was, then the surface waves would travel with this speed. Okay, so this has been calculated using the forward physics modal approximation. Now, when we solve the inverse problem, we just observe the speed of the surface waves, and we want to infer from that what is the subsurface structure. So we pass this dispersion curve on the right into the neural network on the right-hand side. We give it a random draw for the latent variables, and we predict the velocity model on the left. But we know that we want to find the distribution of velocity models, so we do that many times, maybe 1,000 times, with different random draws on the latent variables. So we get 1,000 different samples of the velocity model. And in this case, for this particular dispersion curve input, this is the distribution of velocity models that comes out of the invertible network. And you can see that so the color coding is the velocity structure at each depth. And you can see that the warmest colors are indeed matching the true velocity, which is shown in red, at least down to about 1 kilometer's depth, quite well. And here in the middle, you just see these color distributions represented in different ways, a bit clearer to see. And these are the marginal distributions of the speed of the surface waves at each of the different depth intervals that we're considering. And you can see that the velocity is increasing with depth, as we expect in the Earth, just due to the increase in pressure. Now, the nice thing about this neural network is it took that input curve, and we could run it 1,000 times to get these distributions of properties in the Earth in just 2 seconds. So it was very, very fast after training the network. Now, we don't know if this is the right solution yet. And so we solved the same problem using the Monte Carlo methods that we introduced earlier. And this is the solution that we got from the Monte Carlo methods. And so you can see, again, similar patterns of colors. It's not identical. And if we look at the marginal distributions, they're perhaps a bit more, well, they are more peaked and narrow from the Monte Carlo in the upper layers, but they're centered on exactly the same place. They're biased in the same direction. And as we get deeper layers below a few hundred meters, really the distributions are very, very similar indeed. The main difference is that the Monte Carlo took 3 hours to run to obtain this result, whereas the neural network took 2 seconds. Now, because we're getting lots of samples from these distributions, remember, we could have got this information from the mixture density networks. They're very good at giving us the marginal distributions of the variables and the means and so on. But what we couldn't get from them very easily were the correlations between these parameters. Now here we've got lots of different samples on both sides here, the Monte Carlo and the invertible network. We have lots of samples so we can calculate the correlation or covariance between the samples. And if we just look at that for each of these methods, as shown here. On first glance, they look a bit different because the Monte Carlo is this big block of intense colors here, which isn't represented over here by the network. On the other hand, if you simply look down the diagonal and then the off-diagonal rows, the first 2 off-diagonal rows, you see that they're very similar. It's just that the invertible network isn't getting quite the same magnitude of covariance as the Monte Carlo is. The next layer as well, we've got blue cells here and blue cells here, again, just slightly paler blue than the Monte Carlo. So we're getting the right sign of the correlation, getting some indication of magnitude. It's just not quite as good as the Monte Carlo results. But that's okay because the left-hand side was found in 2 seconds. What's more, the left-hand side was very hard to obtain from our current workhorse, which are the mixture density networks. The right-hand side here will give us a more accurate answer, but it takes 3 hours. That's fine. However, there is still a problem with these invertible networks. And that's because what we find is that they don't work well when we move to higher dimensionality. So we don't just want to use these for inverting the depth profile from dispersion curves. We'd like to use them for 2D, even 3D tomography. And we find that when we add in more and more model parameters, the cursor dimensionality is such that we simply can't, that this, in fact, it turns out that what happens is that this measure here, the MMD measure, is problematic. It simply doesn't have the sensitivity of the difference between these distributions that we require in order to update the network appropriately. Essentially, at higher dimensions, this particular measure of the difference isn't very sensitive. So we then introduce a trick from the mixture density network literature. Instead of using this particular measure, we use one shown here. It's a bit more complicated, but essentially what this is doing is taking the output distribution for y and y dash that we want, is passing it through the network in the inverse direction, and it's testing it against the prior that we know we should obtain. And this determinant here is simply dealing with changes in volume due to go between the left and the right and the left side. And this measure is, instead of using the MMD, what it's doing is it's maximizing the prior likelihood of our two distributions over there on the right. And this, we know from the mixture density networks, is much more sensitive in higher dimensional space. So we're going to use this now and test it for imaging problems. So here we have a 2D imaging problem. We parameterized our model as shown here in 10, I think 11 by 11 cells, so over 100 dimensions. We've got in black here our receivers, just like yesterday, and these are going to be used as sources and receivers. And we're assuming we've got travel time measurements between each of these pairs of stations or receivers here. And so for this particular randomly drawn model shown here, which is from our uniform prior, each speed here in each cell is drawn from a uniform prior distribution. For this particular model, we would have this set of travel times shown over here on the right. And this is just a matrix that shows the travel time in color between any particular source and any particular receiver. And so this matrix of travel times is the data that we could record in the field. And we would like the network to output the distribution of velocity models on the left. To do that, we had to introduce our usual random latent vectors. And then we train the network on, again, 100,000 training data, which are examples of models drawn randomly. They all look like this in character, all speckly, and all have travel time matrices associated with them. So now let's look at that trained network and test it. And we'll test it on our standard 2D test example, just a low velocity circle inside a high velocity background. And the circle being defined on a much finer grid than we used for the inversion. So the circle is definitely not within the parameterization of our models. Now, this particular circular structure has these travel time data that we would measure. And so now we just pretend that we don't know anything about the true structure. We simply pass these travel time data into the trained neural network. We run it 1,000 times and we look at the histograms, or we look at the properties of all those samples to calculate the mean structure and the standard deviation of the structure. Again, this takes about 2 seconds. And so the mean structure has this low velocity. It's not identical to the true structure, but neither should it be. It's a mean structure. It's not a model in itself. It's a statistic of the family of models. The standard deviation structure has the same, is the same as the structures we saw yesterday. It's got low uncertainty in the middle of the low velocity zone, and it's got a halo or a loop of high uncertainties around it. So these are the uncertainty loops that we saw yesterday. They look a bit different to the ones yesterday because here, in this particular example, we used a square receiver array, whereas yesterday we were looking at circular arrays. We'll look at them again a bit later. But nevertheless, we see the uncertainty loops that we expect to see in these tomography problems. Now, we still don't know if this is right, so we ran a Monte Carlo for the same problem, and this is the solution that we got. So it's not exactly the same, but it does have the same low velocity feature, and it does have the same uncertainty loop around it, perhaps with a little bit more structure in it. This one might be better, but it took us 3 days to run, not 2 seconds. And then we can compare the covariances again between these two models, and what we see is that on a broad level, they're similar, although the magnitudes again are slightly less extreme in the network output compared to the Monte Carlo. But you can see the Monte Carlo sees this sort of main sort of 5 diagonals on the structure with the structure in between around the diagonals, and you can see that is the same thing here. 1, 2, 3, 4, 5 diagonals, some structure around it, just values are weaker on the left and on the right. And we can look again at a more complex structure. If this was the true structure on the left, then the travel times would be given by that matrix. If we pass those travel times through the network, we find this output for the mean and for the standard deviation over here. And the mean, as you can see, gives a fairly good representation of the model now. And for Monte Carlo, we get something that looks reasonably similar on the mean side here, but it takes longer. And again, similar matrices. So as an interim summary just now on the invertible neural networks, we've changed the loss function to this maximum likelihood loss function. That allows us to estimate posterior PDFs from these higher dimensional imaging problems. The networks can solve many problems as you like, very, very rapidly after they've been trained. Now, you see statements like this all the time in the neural networks literature and talks, but they don't mean that much unless you know how much time it took to train the network. So you have to account for that. Now, it might be true that you're going to solve so many problems that the training time becomes irrelevant, or it might not. It depends how long it takes to train. What's interesting about invertible networks in the imaging problem I just showed you is that the training time for that network was almost as small as the time it took to run one Monte Carlo inversion. In other words, for almost the same compute time, you can run one Monte Carlo inverse to get one set of results, or you can train a network which will give you results, approximate results, for any number of tomography problems in the future for the cost of a couple of seconds of computation. And that is new. We have not found neural networks that have that third property before in our work. So it seems to have a very stable training process. So at that point, I just perhaps, are there any particular questions brief questions on the neural networks? And then perhaps we can have a quick 5-minute break before we go on to variation using normalizing flows.
So we have one question from Rabindra in chat box.
Okay.
In 1D velocity model, velocity is decreasing at few depths, while in dispersion curve, velocity is increasing.
Yeah. So the dispersion, each period of oscillation in a surface wave is sensitive to the average velocity over a depth range that extends normally from the surface down to some depth. So because these are love waves, so they're most sensitive to the surface, and then they average their sensitivity down to some depth, and that depth increases with increasing period. So the reason it carries on increasing, that dispersion curve, I mean, they don't always continue to increase, sometimes they decrease, but it's just that it is averaging over greater depths. And so even though there's a low velocity zone, the depths around it will have higher velocities, and that's what you're seeing in the dispersion curve. Now, there are cases where the low velocity zone is so extensive that actually in the averaging, you do start to see the dispersion curve go down, but it has to be quite extensive to see that above the overall trend of increasing velocity with depth, which we almost always see in the Earth. So are there any other questions or, sorry?
So students, you just make clarifications if any doubts so far, because after that there will be a small break and then we'll follow the next variational inference and normalizing flow.
Great. So should we have 5 minutes or so, Salman?
Rabindra is from our department, students.
No, sorry. Shall we have a 5-minute break now, or how long would you like?
5 to 10 as you wish. Means.
Okay. Okay. So at 5 past, then I guess. Oh no, sorry. Of course, the time is different for you.
Yeah.
5 past the hour.
Okay. We have the 5 minutes break, then we'll again meet.
Okay, great. I think
There
there's another
is some
question.
questions that is there any chance of biasing in objective function?
So I'm not quite clear what you mean by that, but I mean, the objective functions that you choose, I suppose, yes, you can bias the solution, but really what you have to do, if you mean by the objective function, I presume you mean the loss function used to train the networks. I mean, you should train those loss functions, you should design those loss functions so that you can show that the result would be the posterior distribution. So it's not just as simple as taking a misfit, any old misfit of the data to the model outputs. In this case, you have to use a loss function that's designed so that it does produce the posterior distribution, in which case it's by definition unbiased. So there's a bit more stringent condition on which loss functions or objective function you use to train the networks. But they're given in the literature, and the ones that I just showed you are perfectly good for training the networks that we've tried anyway.
So if there is no other questions, then we can take say 10 minutes break.
Great. Okay. So see you in a few minutes.
Oh.
Bye.
Should pause your recording, Swami. You should pause your recording. Shwaman, recording ta pause kar.
Okay.
Method for this. Yes, so we use a very similar method to most people in this. We have one set of parameters that we use to train the networks directly on, another set that we use that aren't used directly for the training, but they're used to check how well the network has done periodically. And typically what we find is that if you train for too long, the network will start to get worse on that second, in its performance on that second set of training examples. And then we also have a third set that we use that helps us to determine or try to optimize the structure of the network. So the choice of how many internal layers, what size they are, the choice of activation functions and so on. So that's fairly standard way to do this. And essentially you can keep training until it starts to deteriorate on the one of the test sets. So that's how we train them. So hopefully that answers that question. And then what we're going to do in the next section of the talk is move on to normalizing flows. So this is a different but connected way to solve inverse problems. Now again, in this section of the talk, we're going to be trying to approximate or estimate the posterior distribution on the left of Bayes' rule here. And in variational inference, as I explained yesterday, what we try to do is to approximate this distribution using a simpler probability density function Q, chosen from a family of simpler distributions, which here we're calling capital Q. So in other words, we'll start by defining the family of distributions. So for the simplest case, let's say we took the family of all Gaussians. And then we would try to find the particular Gaussian, small q, which best fits the posterior. And that's an example of a typical workflow in variational inference, where we're trying to find the best approximation within a family. And the thing about these distributions is they're parameterized in some way. So yesterday we looked at two variational methods. So ADVI really did use a log Gaussian distribution to approximate this. And in pictures, so let's say that this is the posterior probability density function. Now we don't know what shape this has. This is what we're trying to find. That's our target. So we define a family of different distributions that might have all sorts of different shapes. And we're looking for the particular member of this family on the right that best approximates the posterior. And so yesterday we looked at ADVI, which used the family of essentially log Gaussians on the right-hand side and tried to find the log Gaussian that gave the best fit to the posterior on the left. And then we also used time variational gradient descent, SVGD, which instead of using any particular functional form here, used a set of particles or samples to represent the family on the right. And then we shifted those particles around iteratively to find the optimal distribution of particles that best fit the posterior on the left. So in both cases, we've got some sort of family of distributions that we can represent, given however we parameterize the right-hand side, and we look for the one that best fits the posterior on the left. Now, to do that in variational inference, as we saw, we have to have some measure of misfit between the two and then minimize it. So yesterday we used the Kullback-Leibler divergence, which is just a measure of the difference between two distributions. And the criterion we used was to minimize the Kullback-Leibler divergence between Q, the distribution on the right, and P, the distribution on the left. And I've written it out in a shorthand way compared to the way I wrote it yesterday. But the main property of the Kullback-Leibler divergence is that instead of minimizing this distance between the two distributions, we can instead maximize what's called the elbow, or the evidence lower bound, which was these two terms, given by these two terms over here. And when we maximize those terms, which are much easier to calculate than the Kullback-Leibler divergence, when we maximize those, we find the particular distribution, as shown on the top, which is the best fit to the posterior distribution on the left. The elbow here stands for evidence lower bound, and the key is that we have to be able to calculate that expression there and then maximize that one, which is equivalent to minimizing the Kullback-Leibler divergence. So the question is, how are we, in this third set of variational methods that we're now looking at, normalizing flows, how is it that, what's different about it? How are we going to parameterize the distribution over on the right to make it even more flexible, even more able to be fit to the posterior, or more efficiently able to be fit to the posterior? The way that we do this in normalizing flows is to start with an initial distribution. So our reference distribution, this could just be as simple as a Gaussian, for example. So it could look something like this. And we're going to apply a series of transforms to this, which will convert it into some other distribution, QK, which we're going to try, and using these transforms, we're going to try to warp this initial distribution into a good approximation of the posterior. So now we're using transforms of the initial distribution to try to warp the distribution to something more useful. And these transforms are called the flows. And so we can think of these transforms a number of different forms. So for example, we could have one that simply squashes the distribution. We could have we could take that, the result of that transform, and then apply another flow which separates the distribution along a plane. We could have another flow that pushes the distribution away from a pole. And by applying these transforms in series, one after the other, we can generate very complex probability distributions from the initial one, which is just our initial Gaussian in this case. So how this is actually achieved in practice, or that for any sample M0, if we have samples of the initial Gaussian, we can propagate those samples through the flows, these functions that we've used to warp the distribution, to F1, F2, up to Fk, so k different flows, and we gather them together and just call them capital F. So F represents the set of flows. And what F does is it takes our initial samples from our reference distribution and converts them into samples of our new distribution, QK. That's actually what happens mathematically. Now, since the samples of M0 converted to samples of QK, we can represent that using this equation here, which says that Q0, the probability of any sample from Q0, must be equal to the probability QK in the final distribution of this transformed sample, multiplied by this determinant here. And this determinant is important because it characterizes the volume change for any particular little element of the parameter space here. It characterizes the volume change connected with warping the distribution here. So for example, if I was to go from this one on the left to one on the right, you see that what was a high probability region there has been warped into a low probability region on the right. So essentially what we've done is we've thinned out the space there. We've pushed the distribution, the whole of parameter space apart. And so we've pushed the probability that was here into the two sides. And so that's going to have a volume change. And that's what's given by this term here. Now we've written this term out here as the capital F, which is a combination of all the flows. If I just expand that F a minute, this determinant changes into the product of the determinants of the individual flow functions. And what's important about this expression is that it shows that every single flow must be invertible. That is a fundamental property of the flows, is that we need to be able to calculate their inverses for this to be a valid set of transforms. So I'm going to take this lower equation here, and I'm just going to take the log of both sides of it, which is going to separate up the product into a sum. I'm just going to put that, the result of that, at the top of the next page. So here's the log of the left-hand side, the log of the right, and there's the sum of logs of determinants. What we want is that we're going to design the flows so that this final distribution gives a good approximation to the posterior. And to do that, we know that in variational methods, we have to maximize the elbow with respect to these flow functions now. In other words, we're now going to optimize by perturbing these flow functions using optimization such that we maximize the elbow, which is the similarity between these two distributions here, the P and the QK. Now, in order to be able to do that, we need that these flows are perturbable. Okay, so we're going to have to choose our flow functions carefully because they've got to be functions that we can adapt easily. And so they've got to be invertible. We know that from the previous slide. They've also got to be expressive because we don't know what shape the posterior is, so we need them to be quite flexible. And we also need easy calculation of the determinants. That's important. You can see the determinant appearing up here. Now, it turns out that we already know a function that satisfies two of these, the invertibility and the expressiveness. We looked at the one previously. And it's this function here. This is a very flexible function, the one that we used for the invertible neural network. So it's certainly invertible and it's certainly expressive. We've shown that. But what about this determinant? Well, it turns out, remember, these were very simple equations relating the left-hand side to the right or right to left. And it turns out that their determinants in going from x to z is very simple. It's just the exponential of S2. And the determinant in going from z to y, to the output, is equally simple. And so we can chain these together and calculate determinants very, very quickly. So this structure here is what we're going to use for each of the flows. And we can chain as many of these together as we like to have a more complex and flexible system. That's up to us. So graphically, the way this is going to work, we've got an unknown distribution, which is the posterior, that we want to approximate. So we don't know what that is. It's out there. We've got some initial distribution, Q0, which in our case will just be Gaussians, but it could be anything that's easily parameterizable. And we have some initial estimate for the flows, and this might even just be random neural networks put into this invertible neural network coupling structure. And under that random initial set of flows, F1, we transform the initial, what they do is they transform the initial distribution into this distribution QK that's shown in the middle. So then what we need to do, it turns out, to calculate the derivatives that help us to update the flows, we have to take a few samples. So we're taking the order of 20 samples, a very low number of samples here as the initial distribution. We pass them through the current flow functions to get samples of QK. And that is enough to help us calculate the gradients of the elbow with respect to the flows. Now, once we have those gradients, we can perturb the flows in the direction of the gradients. And that allows us to update them, which gives us a better approximation to the posterior. And then we take another set of samples, we calculate the gradients, which allows us to update the flows and get a better approximation. And we just carry on doing this until this optimization reaches a sort of plateau, so it's not improving anymore. And then that's given us the best approximation that we can have to the true posterior within the family of functions that is representable by the flows, so by the particular structure that we've used. So that's how it works. And in the end, what's interesting about this is we end up with an analytic approximation to the posterior. We've got an analytic initial distribution, could be a Gaussian. We've got analytic functions for the flows. So if we if we chain these two together, we get an analytic description of our approximation. And that has some nice properties in itself. Now, I just want to spend just one slide here comparing invertible neural networks and flows, because in both cases, we're now using these coupling structures. So it looks as though the flows have now essentially become invertible neural networks, but in fact, they're quite different. And we can see that because if you think back to the last hour, the invertible neural networks are trained to learn the relationship between data and model spaces. So essentially, once we've trained the network, we should be able to put in any data on the output side and predict the distribution of models that are consistent with that data. And that means we're training it over the whole set of problems that we might encounter in future. And we do that by using this loss function, or the one where we replace the MMD by the maximum product. On the other hand, in flows, that's not what we're doing. So in flows, we are just trying to find an approximation to the posterior PDF for one specific data set. It's a far more limited objective. We're not trying to solve the same thing at all that the invertible neural network is trying to solve. And the advantage to this is that while the invertible neural networks have to consider all of the different problems that they might encounter, which inevitably then incurs the curse of dimensionality, in this case, since we fix the data to the observed data and then we're trying to approximate the posterior, we're only having to sample or to explore the part of the parameter space that's consistent with that set of data, which is a much more limited subspace. And it's done with a completely different loss function, with this Kullback-Leibler divergence between the two distributions. So even though these use the same coupling structure, don't be confused, they're very different in their objectives and what they achieve. So let's have a look at how they work in practice. So first of all, we'll look at a synthetic test, and it's going to be our usual one, travel time tomography. There's our low velocity anomaly, our high velocity background. Inside a set of receivers, we have travel times between all pairs of receivers. And note we're back to the circular array now, similar to yesterday. And we use the travel times and we pass them into the flows, and then we update the flows to best approximate the posterior. And here is the result. Normalizing flows give us a mean structure at the top and a deviation at the bottom. And just as yesterday, we see the low velocity anomaly surrounded by a halo of slightly lower velocities, with high velocities in between and outside again. And on the uncertainty side, we see low uncertainties in the middle, and then two halos of higher uncertainties. So if I just put the results from yesterday's Metropolis Hastings beside it, we see very similar results. Indeed, if I put all of the results from yesterday beside it, we see SVGD also got very similar results. So we're now almost certain this is correct. Plus or minus a little bit of noise or variation between them. ADVI gives the right mean. Standard deviations are a little bit biased, so we still see a slight loop of higher uncertainties here, followed by low uncertainties, and then a slightly higher loop of uncertainties, but they're certainly a bit different from these ones. So not such good representations of the uncertainty from ADVI. But we're now really certain, firstly, the right solution, and secondly, normalizing flows here to work. So now if we just consider the computational cost, so we're introducing yet another algorithm here. So what was the point? Well, that's shown in this table, where we've just ordered the methods by the cost of getting those solutions, and the cost is in terms of number of forward simulations. ADVI wins in terms of number of simulations. It gives the correct uncertainty result. So out of the others, this one, by at least an order of magnitude, is normalizing flows. Now, it must be said that the comparison here may not be entirely fair, because it's actually quite difficult to detect convergence of Monte Carlo methods. So perhaps these Monte Carlo runs converged earlier, but we kept them running for a factor of 10 too long or something. So it may be that these are cheaper. But there is one test that we can do to objectively compare Monte Carlo to normalizing flows or SVGD. And that is, let's give the same Monte Carlo method only 30,000 evaluations or 400,000 evaluations and see if they do as well as these two methods did in producing the solutions. So we took the Metropolis Hastings algorithm and gave it 30,000 evaluations on the left, 400 on the right. And you can see for 30,000 evaluations, it has a hint of the low velocity region, that kind of splodge, no information in the uncertainty. So that isn't working. Even after 400,000 evaluations, although it's got a mean structure that starts to look roughly correct, the uncertainty still is nowhere near what we're trying to find with the double halo. So this genuinely does then indicate that this isn't just a bias of us making these numbers from Monte Carlo too high. Two variational methods give the correct results, normalizing flows and SVGD, and they are significantly cheaper by 1 or even 2 orders of magnitude than Monte Carlo. So let's have a look at this just on a real data example. Here are the station distributions that we looked at yesterday. Again, we use interferometric methods to find the travel times between all these different stations, and we use them for tomography. We did this yesterday for the first 3 methods, and now we've done it for normalizing flows as well. So now just line up all those solutions. Here's ADVI, SVGD, Metropolis Hastings, and normalizing flows. The mean structure is at the top in each case, and you can see that the mean structure is fairly similar, and it's got all the different features that we expect. We can see this is the flow solution that we're evaluating now, so you can see the fast Scottish Highlands, the slow Midland Valley, the Southern Uplands, the Irish Sea, just as we did yesterday. All these same geological features are there. However, it appears that, normalizing flows and Metropolis Hastings are given very, very similar models. If you look through sort of piece by piece, they're really quite similar. SVGD and ADVI appear to be giving us slightly lower resolution mean models. If we look down at the uncertainties on the bottom, so this is just a standard deviation, these all look a bit different. However, if you look at the right-hand 3, what you see is that in each one, there tends to be these, for example, 3 low uncertainty regions here. That's visible in all 3 of those models, slightly different magnitudes, but nevertheless they're there. A low uncertainty region up here in the Irish Sea, and low uncertainty up in the Highlands. So similar types of structures, just different magnitudes. And perhaps as expected, ADVI also has those features just visible, but it does seem to give biased uncertainties. So in this example, again, if we look at the cost, again, we see exactly the same results, that the SVGD and normalizing flows appear to be giving by far the most efficient way to estimate these uncertainties. So that is the section on normalizing flows and invertible neural networks finished. Now, oops, I just realized I shared the wrong screen. 1 second. Let me just share what should be being shared right now. It's popped out of the presentation. Hopefully now you can see we've gone back to the main slide. And so the final section of the talk is, how do we bring all this together? We've now got a very good idea of how these various methods perform. They all give estimates of uncertainty, some better than others, some more efficiently than others, but they all give estimates of uncertainty. How do we use all of these methods to answer questions about the Earth? I mean, for a start, should you choose one? And if so, how? How do you choose a method? And my view is that you don't choose a method, you use them all. You just line them up and use them all, or any that you can. And I'll show you why through this last section, which is an interrogation theory. And this will show there's a very good reason to use multiple methods. So in this section of the talk, I'd just like to give special credit again to Shubin Zhao and Jin Zhang, who you've seen before. And on the left, also Richard Arnold. And Richard comes from Victoria University in Wellington in New Zealand. And he came across to Edinburgh to do a sabbatical with us. And it was during that time that he and I worked on this interrogation theory. So Richard is a statistician. He works more in medical statistics and epidemiology now, but with the government in New Zealand. But in this case, he's also has a history of working in geophysics. So what we want to do in interrogation theory is answer real-world questions by interrogating data. And so far, through all of yesterday and today, we've been trying to work out what are good algorithms to interrogate data for high-dimensional parameter spaces. But in the end, we want to answer questions about the Earth, and typically, these are often low-dimensional answers. What is the volume of this subsurface reservoir? Well, that is a single number, single-dimensional answer, x kilometers cubed. Is there a thermal plume beneath this area for geothermal energy? It's a binary answer, yes or no. What's the depth of the moho here? Again, a single number, z kilometers. So the answers that we want are very low dimensional, if not one dimensional, or even binary. The problem is that those low D answers often lie within high dimensional spaces. So the kinds of models that we've been looking at in the last couple of days. So what we've done in interrogation theory is we've gathered together a lot of, or several fields which traditionally are used in sort of disparately or one after the other, let's say.
Your
and we put them together.
visible. Screen is not visible, is it? Are you? Is everybody able to see the slides?
No, screen is not visible.
Yeah, we're not seeing any slide.
Oh dear. Can you see it now?
No, still.
Yes.
No.
Oh dear. So can you see the list of topics now on my mouse?
Yeah. Yeah, this is good. Yeah, this is good.
Okay. Very sorry. Right. I'll just quickly go through. These are the guys that I gave special credit to: Richard Arnold on the left, Shubin Zhao in the middle, Xin Zhang on the right. And in interrogation theory, what we're after are low-dimensional answers to these kinds of questions. Apologies for that. These are the slides that I was showing. So what we're looking for are the answers to these kind of questions. What's the volume of my reservoir? It's just a 1D answer. Is there a plume? Yes or no? What's the depth of the moho? Z kilometers. These are one-dimensional answers to important questions in earth sciences, but the answers are buried within high-dimensional models like this one. And so in interrogation theory, we've tried to bring together a bunch of methods to focus on the questions of interest, not on the model parameters of these tomograph models. So if we compare that inverse theory, which is the usual case, we construct forward problems between parameters M and data space B, and then try to solve the inverse problem, given some measurements B, what is the family of parameters that fit the data or are consistent? And that's what we've been doing so far. In interrogation theory, we focus on a question or a set of questions, and they are going to be the focus of the entire methodology. So the questions will be Q, the answer is A. And given this particular set of questions and the corresponding space of answers, we're going to first define a set of forward models and parameters. And in particular, these parameters have to be chosen such that we can answer the questions from those parameters M in some way. We might have multiple forward models. The parameters might take multiple forms. It might not just be seismic parameters. You might have EM parameters with EM forward models as well. So we might have multiple forward models, multiple sets of parameters. These give us a forward problem from which we can solve a design problem, which means we're going to design the experiment that we want to perform using these multiple data types, perhaps multiple forward problems. And this is going to define our data space. After we've solved the design problem, we perform an experiment or an expert elicitation or some combination to gather some data. And at that point, we then solve an inverse or inference problem as we've been discussing. But at this point, we haven't finished because we haven't answered the questions. In order to answer the question, we have to take all of this different data on the design, the data set, and the parameters and solve a decision problem. And it's that decision problem that gives us the answer. And throughout all of this, if there's one thing we've learned in the last couple of days, it's that we've got to consider multiple algorithms because different algorithms give us different answers. So if we want answers to our questions which are unbiased, we shouldn't choose a single algorithm because every single algorithm is biased. It's only the combination of algorithms that gives us some sort of idea of the spread of solutions. So this is what we'd like to do in schematic form, just in a bit more detail. Here's how it works in workflow. I'm getting an odd, it's not, are you seeing the workflow diagram?
No.
Okay, I seem to have a problem here. Let me, okay, I'm going to change the, okay, let me stop the share. Oh, what happens if I resume the share? Oh no, that's gone back to that again. Let me come out of this and share again. I'm sorry, we haven't been able to see anything I've been talking about. Okay, can you see now two diagrams?
Yes.
Right. Okay, I've been talking about the difference between inverse theory on the left and this interrogation theory on the right. And in interrogation theory, we've taken the forward and the design problem and essentially focused them around particular questions of interest Q, which defines a particular answer space A. Once we've designed an experiment, we conduct an experiment which gives us data, and that allows us to solve the inverse problem with parameters. But the important thing now is that for any particular questions, we might have multiple forward models, multiple parameterizations, and so multiple sets of these solutions. At that point, we still haven't answered the question. For that, we have to solve a decision problem, and I'll show you how we do that in a minute. And that decision problem is basically deciding between different answers in the answer space. And in all of this, we have to consider different algorithms for solving the problem because we know that they give us potentially different answers, different qualities of answer. So in interrogation theory, we include all of these different possibilities and we bring them together in a consistent way to answer the question. And that is going to, as we'll see, it's going to minimize our bias in the answer. So if I keep talking and you don't see the slides change or something goes wrong, please just shout at me and because you should see the slides changing pretty frequently. Okay, hopefully now you can see the start of a workflow diagram.
Yes.
Yeah, good. So the way this works in practice as a workflow is we start with some background knowledge, and we have our particular questions of interest, and we want to get to the answer space A down the bottom. So given the questions, as I said before, we define a set of forward models such that the parameters would allow us to answer the questions in one way or another. We'll then design an experiment, and ultimately then we go off and calculate or collect some data. And from this now, we want to answer the questions. To do this with decision theory, what we have to do is define a utility function. This is how decision theory works. And the utility function is a special function that defines the net benefit of choosing one answer A over any other answer A. So for any particular answer we might choose to give to the questions, the utility function determines whether one answer is better than another. And this utility, therefore, is to be maximized. We want to find the answer that maximizes the utility function. Now, that all makes sense. Utility function, the answer here depends on the models, the forward functions, the data, the design, and the algorithms C. It's easy to write that down, but it's actually hard to maximize it because this is a very complex set of dependencies. We've got multiple forward models now, multiple designs, multiple algorithms for sure. So what we've done in interrogation series is introduced an interim step, an interim space called the target space. And so what we do is we define a target function T, which takes any particular model M, and it converts that into some value in the target space, or set of values in the target space. And the key property of that target space is it's as close as possible to the answer that we want. At the very least, it's relatively easy to answer the question from the values in that target space. In other words, if we can define this target function appropriately, then the decision problem becomes a lot easier, because now our utility function just depends on the target values and on the data set. So the utility now is far easier, and we can write it down and maximize it much more easily. So that's the way the workflow works. Let's put it over to the side and just be a bit more explicit about the utility. So the utility here, we're going to use a simple squared utility for this talk. And what it says, the way that this is defined is, given a particular value for the target variable, so this is the value in the target space here, utility just depends on the target space now and not all the rest of the detail that happened back here in the algorithm or the methodology. It only depends on that target function, and the utility says, well, if that target value is true, what is the utility of my various answers that I could give? And then what we'll do with this utility is we'll look at averaging it in some way across the various target functions. And the reason we look at the average is that we can show, we showed in this paper, that the average is the optimal answer in the sense that it's least biased. So within all of this framework, just taking the average of the utility of these target functions is least biased for this particular utility function. Now, this particular optimal answer, we can expand it into an equation which looks a bit complicated, but in fact, it's quite simple when you just look at the terms individually. So this one over on the right here is the posterior PDF that we have been estimating for the rest of the talk. Is the probability of the model given the data. The only difference in how we've written it down here is that we've now got dependencies on what algorithm we use, what forward functions, and what design. This part here is simply the target function that projects that model into the target space. And then this part over on the left is just the probability that any particular algorithm or forward function would result in us getting the true posterior PDF. So that's accounting for the approximations introduced by the algorithms and introduced by the forward function. And the sum over here means that we are including all of the different algorithms and forward functions that we've considered in our problem. So the nice thing about this is that it shows the difference between inverse theory, which is estimating this probability density over on the right, and interrogation theory, which is calculating everything around that in order to find an optimal answer to a specific question. And the specific question is going to be encoded in the target function. What's clear from this is that we need to estimate uncertainties. And that's why we've been spending so much time on uncertainties. So now let's have a quick look. I know time is now running out, so just I'll give you a quick look through one example. I'll show you a synthetic example, and then I'll just show you the results from a real data example, and then we'll stop. So here's our standard synthetic example, and we've just looked at all the solutions when we try to image that structure using the receiver array around it. We get these different solutions for the mean on the top and the standard deviation on the bottom from 4 different algorithms: Metropolis Hastings, SVGD, normalizing flows, and ADVI. Here's a question: what is the area of that low velocity anomaly here? Well, we can look at it and we can say, well, it's about this size, isn't it? But that's not really good enough. If this was a valuable resource in the subsurface of the Earth, we would want to know pretty much exactly what size that is in order to do value calculation. So now we have to do something a bit more formal. So the first thing is, we're interested in this low velocity anomaly, not any anomalies that occur out here. So we're going to put a mask on the model and just say we're focusing on the middle part. And we want to know what's the boundary of that. So we mask it out, and now we look back at our methodology and we define various parameters here. These ones were defined throughout yesterday and today. We're going to use the fast marching method, travel times, standard seismic velocity, and uniform prior in each cell. The receiver station locations are going to be fixed, and the data are going to be the travel time. That's what we've been using all along in this seminar. Now, we have several algorithms now, and for each of these algorithms, we have to define the prior term that occurred in that long formula. And this is the probability that each algorithm will give the correct solution. Now, the one thing we know about the algorithms is that these 3 over here tended to give roughly what we think is the right answer. And ADVI gave an answer which gave a mean structure very, very efficiently. But the uncertainties seem to be biased. So we're going to give that a lower prior uncertainty than the others, but otherwise we'll just treat the others, we'll give them equal uncertainty, equal probability of giving the right answer. And the probabilities here add up to 1. That's why they are these values. The target function is going to be a function that transforms any model into the area of low velocity zone. That's what we want. And the optimal answer using the square utility is just going to be given by the formula that we had previously. So in order to find that optimal answer, we have to define T, and that's going to give us the area of low velocity anomaly. Now that's not easy. Here is a model. We need to be able to apply this to any model, and every model sample looks like this. So what's the area of the low velocity anomaly here? Well, in the masked version of it over here, what it comes down to is saying, well, is this cell here, or is each of the cells in the low velocity anomaly or not? Is it low or high velocity? And for that, we need to answer the question, what threshold are we going to use? And of course, we can completely bias the answer of the area of the low velocity anomaly just by changing that threshold. So we need some way to define this in an unbiased manner. So we now have a sub-question or a sub-problem. What threshold should we use to discriminate low from high velocities with minimal bias? So now let's answer that question. The way we can do that using the data is we take some cells in the solutions which we're pretty sure are on the inside and on the outside. We don't know all the cells on the inside or outside, but we know some because these cells tend to have low velocities, the one with stars, and low uncertainties. These cells with crosses tend to have high velocities and still low uncertainties. So these various sets of cells, we're reasonably sure are inside and outside of the low velocity zone. So let's put them over there. Each of those cells, we know from our posterior distribution, we know the marginal distribution for each of those cells. And so here I'm just showing you the set of different marginal distributions from the Monte Carlo run for all the cells on the left here, which are in the blue, or the high velocity regions, and the marginals from the cells in the low velocity region. If we want to find threshold which optimally discriminates these cells from those ones, what we can do is we can calculate the average cumulative density function on the left and the right. And this is a function which says, okay, for any value, say 1 kilometer per second, what is the probability that the low velocity cells in the middle have a velocity that's lower than 1 kilometer? That's what this curve tells us. And it tells us the probability that is about 0.4. And similarly on the right, it tells us what's the probability that the high velocity cells are above, say, 2.5 kilometers or above 1 kilometer. That's given by the probabilities here. And if we take those CDS and we put them together, this particular point here is important because that is the point at which the probability of putting the low velocity cells, categorizing them as low velocity, is exactly equal to the probability of categorizing high velocity cells as high velocity. That is the unbiased threshold to use. And what's clear is we need uncertainties to define that. So now our question, is that inside or outside the low velocity, just comes down to, is it less than or greater than this threshold? And we take all the cells that are below the threshold. These are all low velocity cells. However, we're looking for the area of the low velocity anomaly in the middle, so we're not interested in these disconnected regions. We're only interested in the low velocity cells that are connected together. And in this case, for this particular model on the left, these cells constitute the area of the low velocity anomaly. So finally, we've got ourselves a function, target function that converts any model into the area of the low velocity cells. But to get it, we had to use uncertainties to find the threshold that wouldn't bias the answer. So we can now use that to translate all of our models into estimates of area, and each of the methods will give us a different histogram of areas. So we've got 4 different histograms from the different methods. The true value is given in red in each case, and you can see the histograms all include the true value. But we want to come up with one answer. What is the area? Well, we have to account for the prior probabilities that each algorithm will give the right answer. And we have to plug those into that formula that we had previously. And if we do that, where this, I should say, this whole right-hand term is given by those histograms. If we do that, we get this answer, 12.89, when the true answer is 12.56. And we get that answer very accurately, as you can see, even though every single model looks like this. All of the models, speckly, they're all wrong. None of them is equal to the nice circular velocity anomaly, yet we get a very good answer. And we can show that this appears in a variety of contexts. For example, what happens if we use let me just show you the answer. If we, instead of using this fine grid or relatively fine grid that we've been using up to now, what if we use a really coarse grid and just follow the same process? Well, the coarse grid for each of the methods very clearly gives us this 3x3 area for the low velocity zone. And there's not going to be any doubt that would be the area that we get if we just look at the single mean structure. So that gives us a 9 kilometer area with this coarse grid, where the true answer is 12.5. If we just go through the same process with this coarse grid, we define the target function and we translate all the models through with the coarser grid, we get this set of statistics, which is actually pretty similar to the ones from the finer grid. And the answer we get is almost identical to the one from the finer grid. And so what you're seeing here is that even though when we interpret the mean map alone, we got this terribly biased answer of 9 kilometers per second, if we add in the uncertainties, which is usually we think of the bad thing, uncertainties, we get a far, far more accurate answer, even on a much, much coarser grid. And that's the value of the uncertainties. Now, I have an application to the IRC basins, but I think given the time is up, I'll maybe just stop there and pop out of this. Perhaps I can just show the final slide. We should just go back to this slide here, the original one. Just to summarize then, we've been through a number of algorithms, and each of them we've used to estimate uncertainties. But in no way did we really define or make clear why those uncertainties are valuable. It's only when we put them together with something like interrogation theory that it becomes clear that by assessing uncertainties, you actually get far more certainty in the answer to any of your scientific questions. So thank you very much for your time and for coming back again today. And there's my email address. Feel free to use it if you have questions, but please feel free to ask questions now. And as I said, the papers are all available on their website. So I'll stop the share and be pleased to answer any questions if there's any time left.